I'd like to introduce our presenter, Michael Krauss. Michael has more than 29 years of fluoropolymer experience working for 3 fabricators, a resin supplier, a converter, and is currently sales director, fluoropolymer and dual laminates for Knight Materials. He has a bachelor's degree in chemical engineering from the Pennsylvania State University and an MBA from Villanova. He is currently the president of the Dual Laminate Fabrication Association, the vice chair for the Dual Laminate Subcommittee of ASME RTP1, and is the marketing chair at MTI. Now I'm going to turn it over to you, Michael, to start the presentation.
Thank you, Cindy, and good to see everybody online here. As Cindy mentioned, if you have any questions that come up, please send them in the chat, and if they're related to a specific slide, please include the slide number. It'll make it easier to just go back and answer the question and take care of it correctly. Otherwise, at the end, if you have additional questions, my contact information's out here and you can reach out to me directly. Real quickly, a little bit about Knight Materials. Knight Material Technologies, otherwise known as KMT, is the combination of 3 companies with a really long and diverse history solving corrosion issues with non-metallic solutions. KMT is headquartered in East Canton, Ohio, and has over 100 years of experience, mainly with acid-resistant brick and ceramic mortars, as well as ceramic packing, both structured and random. Knight or Electrochemicals, headquartered in Emmaus, Pennsylvania, about an hour west of Philadelphia, and has over 70 years of line steel, fluoropolymer lining technologies, and superior dual laminate products, is located in Maple Ridge, British Columbia, just outside of Vancouver. And finally, we have a facility in Houston, Texas, where we do both acid brick installation and service and fluoropolymer line steel installation and service. So to give a little bit about our company and our locations. When we look at corrosion-resistant linings for immersion service, we're typically trying to find and recommend the most cost-efficient solution that provides a robust system meeting customer design and life expectancy. Why do we use linings? In a lot of cases, they are more chemical resistant than alloys, less fragile than glass, and offer higher temperature ranges than a lot of the elastomers. They're used in a variety of different applications. They can be reactors, storage tanks and vessels, transport systems like tank trailers and ISO containers, and they're used both for protecting the metallic or the outside from the corrosive media, but also in high purity applications where you're protecting the chemical media from getting contaminated with any of the materials or the metal that's providing structure. And our goal is really to match the best material and application to your specific environment and avoid costly failures. And we'll look at service temperatures. And this is an area that is really tricky. We offer bonded sheet linings. So when we look at fluoropolymers, we typically rate them to about 300 degrees Fahrenheit. In some cases, the fluoropolymers might be able to hold up to a higher temperature, but the adhesive system and design can be the limiting factor. So it gives you a good idea around the fluoropolymer solutions, depending on specific chemical concentrations and service, in the 230 to 300 range Fahrenheit. Non-fluoropolymers a little bit lower, and we can actually improve it significantly by combining the Knight technology with the fluoropolymer lining and using the acid brick as a thermal barrier so that the process temperatures can see upwards of 700 degrees Fahrenheit, while the lining, providing the chemical resistance, is seeing a much lower temperature and providing a really robust and unique solution. When I look at the keys to success, I view it much like a table. It's really difficult to say that the material selection, the applicator application, that anyone is more important than the other. It's, again, like the legs of a table. It is critical that they all do well, that they're all strong. Otherwise, you will likely have a problem. We usually see people starting with the material selection. What is the right material? The right solution. And even here, it's not always black and white. There are corrosion guides that are out there that look at chemical attack, but they typically neglect permeation. The preference is using the corrosion guides or material and resin suppliers as a really good starting point. But if you have the capability to do either Atlas cell testing according to the ASTM standards, or even put a line blind flange or manway cover into service, will give you a huge opportunity to get real world data. And it's also tricky looking at the corrosion guides. They don't always agree with each other. So it's understanding everybody's bias and why there may be difference between different results in different corrosion guides. What happens when we do it wrong? And the easy answer is picking the wrong material, the wrong application, or the wrong applicator can lead to premature failure, unplanned shutdowns, contaminated material, and expensive remediation. So it's really important not only figuring out the right material, the right application, but understanding the qualifications of the installer. I'd say from an end user perspective, it's really important to make sure that the RFP, when you're going out, has enough criteria to make sure that you're taking care of all the situations, that you don't just spec out, I need a PTFE lining, and it goes out the door and you get 3 bids back. If you don't know the quality of the installer, it doesn't really matter that you've got the lining material selected correctly. For options, there are a myriad of options that you'll see. Everything from base metals like carbon steel and stainless to exotic alloys, glass lining. Even in the world of fluoropolymers, there's a wide range of options, not only the different materials, but spray coatings, loose liners, bonded sheet liners, rotational lining. There are other thermoplastics, there are rubber linings, there's thermosets like fiberglass that are out there. I believe it's really important for the end user, the specifier, to ask lots of questions. Usually as you start asking questions and understand what the benefits and the strong points are of a specific application or material, you'll also find out what some of the limitations might be. And that will help you build a complete picture for yourself. Understanding, again, that all the people you're talking to, whether it's different applicators or resin suppliers, they all have their own backgrounds, their own bias and perspectives. And it's really incumbent upon you to try and put together the clearest picture possible so that you can make the right decision for your system and company. And again, learning the specific benefits of the different materials and applications will help you get there faster. When we talk about fluoropolymers, and this is where the bulk of my career has been, there's a lot of reasons to use fluoropolymers. First and foremost, they have excellent release properties. We all remember the old Teflon coated frying pans that nothing sticks to, right? And one of the benefits of the fluoropolymers with the release properties are that the process tanks, the lined equipment become much easier to clean. You don't tend to see scale or buildup because nothing sticks to them. In addition to that, you get excellent chemical resistance, really good durability, a fairly broad temperature range. And one of the things that's, I think, unique to a lot of the fully fluorinated fluoropolymers, so what would traditionally be called the Teflon materials by DuPont or Chemours, is what I say broad spectrum chemical resistance. Here, or say comparing to certain alloys, and I'll look at a system that we worked with a customer several years ago. They were bringing in hydrofluoric acid and storing it at 49% concentration. They had an alloy vessel that was holding it, and it worked really good. Their supplier wanted them to evaluate switching from 49% to 70+%, a little more concentrated. They were producing it that way. It would be easier. Our customer was really interested in that, but they had a lot of concerns. Their problem was that if they put the existing tank wouldn't hold up to the 70% hydrofluoric acid. They'd have to put a new and different alloy vessel in to do that, which they were willing to consider. The problem they faced is that that alloy wouldn't hold up to the dilute 49% HF concentration. And here, what we found is by switching to a PFA lined carbon steel vessel that wasn't much more costly than the alloys they were looking at, they were able to handle both the 49% and the 70%. It gave the customer more flexibility. Material selection, again, it's a really challenging source. I mentioned briefly that you must see conflicts with different guides, say PVDF. And you have to understand there are two main suppliers of PVDF resin in the Western world. And the chemical resistant guides that are out there are very different. Once you understand the reason behind it, it makes sense. The first supplier, PVDF, is the highest performing material they make. And they've done extensive work and research with adding additional grades and developing a huge database to know exactly where and how far they can push PVDF. And they tend to be aggressive and push it to the exact limits that they can get away with, because that's what they have. The second supplier has other higher performing fluoropolymers. So they tend to be a bit more conservative. Whenever they get to the borderline areas, they're pushing you to upgrade to a different higher performing material. So the answer, again, it's not black or white, what's right or wrong. It's understanding the bias and knowing where your system is, how much control you have of your process, and whether you can get away with using the data from the first guy and saying, we know our process, we're never going to go outside of the realms of what they're operating at, and we're comfortable with it. Or whether you say, we want to be a little more conservative, we don't know of all of our process controls, maybe we run a little bit hotter than we think, and we're better off upgrading to materials. So it's kind of tricky. The other comment that I will say is that the chemical resistance data that's out there is typically evaluating plain virgin material or sheet. It's not something that has a lot of stress in it. It doesn't have weld. It's not been formed. And those are usually the areas where we tend to see problems first. So looking at the bulk material, it may hold up fine. You might find out that the service attacks the welds. And that goes back to, can you do some testing? Can you make an Atlas cell test and put it in service with a weld line, or put in a line blind flange with a weld to simulate how it's going to work in service and get data not just on the bulk material, but also understanding how it works in service and what the entire system would look like, not just the base material. The other point I'll bring is the chemical resistance guides. The data is purely on chemical attack, and permeation may or may not be an issue, but it's usually not included in terms of the data and the material recommendations from the from the corrosion guides that are out there. A case in point would be if you look at PTFE lined steel. If you look at PTFE and you look at bromine or a variety of brominated compounds, the PTFE holds up really well, but the lined steel typically fails quickly. And the question is, why does that happen? And it happens because of permeation. Bromine tends to permeate PTFE pretty easily and starts attacking on the backside of the liner. So understanding that you look at a corrosion guide and it says it's suitable may not be the whole story. And again, it's why you want to reach out and not just use the data, but talk to the suppliers and applicators. Then in addition to that, when you're looking at material selection, it's challenging not only the chemical, but the fabrication geometries, even the application style starts to play into that manner. You might look at certain materials and if you pick at different applications, certain materials like ECTFE tend to do extremely well and work well for thick film spray applied coatings, and they're used frequently there. Whereas ETFE, otherwise known as Tefzel, has challenges with the thick film coatings, but does extremely well rotational lining, and which leads you, when you start looking at trying to qualify, you might going out to service get a spray coating with one material, a rotational lining recommendation with a different material, and a sheet lining with a third material. So again, asking questions and starting to build your own case is really important to help you make the right decisions long term for yourself and your company. The other scenario that we've seen with is, plug and play, or, should we use the same thing that we've always done before? And I'm a huge believer in experiential data. If you've learned for something and it's been in service, absolutely it makes sense to take that into consideration. But you need to be careful, because quite frequently saying you're making a duplicate isn't always the same situation. A couple of years ago, we were contacted by a customer looking to build a new plant. They had a PVDF dual laminate vessel, and they wanted, using the same service, they wanted to duplicate the plant. The difference that we found out after some discussions is that the original plant was in the Gulf Coast, which typically doesn't see cold weather conditions, and they were building this new plant up in northern Canada, which sees extremely cold conditions. The vessel itself was going to be an outdoor vessel, so if it was shut down, if the plant was shut down for any length of time during the winter, they could see temperatures well below 0 degrees Celsius, probably approaching that in Fahrenheit as well. And PVDF is known to have embrittlement issues at low temperatures. So just because it worked and you're trying to make a duplicate, the situation was actually different. The same type of thing happens frequently in chloralkali service, where the brine streams and feedstocks are different, and even operating temperatures, depending on recycle streams and process conditions, varying 5 or 10 degrees Fahrenheit, can make a big difference on whether one material works or doesn't. So understanding the history is really important, but just blindly moving forward with the same material because it's what you did in the past isn't necessarily the best situation. Yeah. Temperature range is also really important. More often than not, when we get a request to look at something, we're given an operating temperature, which is usually the higher end of the temperature they're running at, and a design condition. And we don't really know, are they thermal cycling it? What's the entire range? What's the lowest temperature it might see? Because that could be an issue. How often are they thermal cycling it? Because that can create an issue. And even looking at the difference between the operating and the design may make a difference on recommendation. If there's a design condition for 150 degrees Fahrenheit and you slap on an operating condition of 150 Fahrenheit and you slap on a design condition of 300 degrees Fahrenheit, you may move up to a much more expensive material. And the answer might be somewhere in between. Maybe you're running at 150 and there's a possible excursion to 200. Well, letting us know, and again, going back to communication, letting us know how it operates, what the real parameters are, will help getting us back to the most cost-effective solution and getting you the life expectancy that you're looking for. It's also depending on the certain lining materials, especially the non-fluoropolymer. So if you're looking at PVCs, if you're looking at polypropylenes, you start to get to an area where there are significant differences in different grades of material, different brands, and they may not perform identically. So understanding what you're asking for, what might work, and how to specify it in a proposal so that you get what you expect is really, really important. The other thing is that the devil is in the details. You might say that we've got a 35% HCl line and think that that's the driving factor, and neglect that there's a bunch of organic chlorides in the ppm level that are floating through the system. Well, those small amount of organic chlorides or other materials might be the difference between success and failure. So again, sharing information, helping understand what the entire chemical stream is, how everything operates, is really critical for success. I mentioned this briefly, but the Atlas cell, the chemical resistant cell test, are a great way to get data. It doesn't cost a ton of money, and most fabricators can make up the samples that need to be tested. There's a bunch of labs that for a couple $1,000s can get you data for a couple months and start to see how the different systems operate in service. Usually these setups can be done where you have the cell tested horizontally, and you've got both a liquid and a vapor stage, so you can really stress the system and get an idea of whether you think this will work or not. And in most cases, you can add welds and other components into the test cell to get a real good, real life version of what happens in service. Looking at process variables, usually people talk about what is the temperature we're operating, what are the chemicals, and what is the concentration. And that's really important. Knowing all of the different chemistries and concentrations is critical, as I mentioned, because some of them can, in small amounts, can make a difference. Sometimes there's intermediary chemicals and reactions going on. So really having a process engineer understand what the system might see, not just what the starting materials are and the end material, can make a difference. Looking at the type of material, is it abrasive? Do you have to worry about abrasion? What type of temperature change are we doing? Are we heating and cooling really quickly? If there's an unintended shutdown, what's the rate of temperature change? Pressure and vacuum will impact both the lining type of selection, but also will have an impact on the vessel itself, the design. If you're looking at fixed equipment versus transportation equipment, there are different requirements. If you've got agitators and other environments, you can put mechanical stress on the vessels. And again, previous experience. What have we used? What worked well? What didn't? What's still available today are all really important in terms of trying to figure out the best solution. Again, the more information that's shared, the higher the likelihood of success for you. As we start looking at materials, we start with, at the base level, some engineering polymers, polyethylene, polypropylene, PVC. And then as we move up through these materials, you tend to see increases in chemical performance and chemical resistance, increases in temperature performance, and as well increases in cost. So you're trying to find the right solution that makes the most cost-effective solution for you. After the engineering polymers, we look at partially fluorinated polymers, PVDF, which goes by frequently the brand name Kynar, ECTFE, you'll hear as Halar, and ETFE, that's known as Tefzel. And finally, you move into the fully fluorinated materials. You've got FEP, PFA, and modified PTFE. One of the tricky things here that tends to be and drives me crazy with one of my pet peeves is Chemours or DuPont, when they develop this material, they use Teflon as their brand name for all of their fully fluorinated materials. And then frequently specs come out for Teflon. The challenge on that is it limits you to only using a Chemours material, but more importantly, it doesn't really tell the applicator or the installer what material you want. There may be cases where you need to use PFA, but someone wants to supply FEP or vice versa, and they're all Teflon. So Teflon, good brand name, great marketing by Chemours, but a really challenging spec, and just something to be aware of on your own is, where it makes sense to spec if there are specific brands or properties that you need, but don't unintentionally limit yourself or create a challenge by not properly specifying something. This is just another quick slide to kind of go through how some of these materials move through the different properties. The caveat here is permeation resistance is also a really challenging topic. And again, it's something to be aware of. It's usually not the decision-making, the specific or primary decision-making factor, but it needs to be accounted for. But it's always on a case-by-case basis. It's not as easy as to say that as you move up through the different materials, one of them is noticeably better, or that you're always moving up and that one is doing better with permeation compared to the lower performing materials. There are cases where the data is surprising, and that a material that we'll say is a much considerably lower cost material actually performs significantly better with permeation. And again, it's all different. So you can't make you can't make a good guess and say that, well, this material performs well with HCl in permeation, so it's going to perform fine with HF or some other material. There's very little correlation to jump between one material and another, and then comparing the different lining materials. As we look at the specific materials, I kind of started here with polyethylene. It's not typically used as a lining material, either in line steel or in dual laminates, but it's one of the most prevalent materials or plastics that are out there. It's got a decent chemical resistance in general to about 85 degrees Celsius, 185 degrees Fahrenheit. What you see here on the right side is the composition. So you've got this repeating ethylene unit, which has got the carbon backbone and a bunch of hydrogens here. When you start looking to see a little more frequency for lining, polypropylene is used as a lining material, both for dual laminates and line steel. Gives you a little bit higher possible upper temperature limit. Tend to think the 100 degrees C is probably pushing it. Generally, I would be, and I tend to be conservative, 90 C is probably a better number for that. But it's got, as far as non-fluorinated material, it's got a pretty good chemical resistance to acids and some bases. It doesn't work well with halogens or aromatic or chlorinated hydrocarbons. And again, it looks similar on the right side again to the polyethylene. You've got the repeating carbon chain. You've got a bunch of hydrogens and some CH3 units as well. The next material to look at is PVC, polyvinyl chloride. Again, non-fluorinated. It's got pretty good overall chemical resistance. The temperature range is in roughly the same range as the polyolefins, polypropylene materials. One of the challenges here is if you're aware of PVC pipe or thick sheet, it's really rigid and strong material. And it's why it's used in a lot of solid piping systems. In order to make it a lining material that we can take it and then bend it and form it either in a dual laminate structure or in steel linings, we need something that's more flexible. And to make the PVC more flexible, it's heavily modified by adding sometimes upwards of 30% plasticizers. So the difference in plasticizers will give significantly different properties in terms of chemical resistance, maybe UV resistance, all sorts of, and how it will hold up over time. So when you start looking at materials like this that are modified, general spec like PVC can be misleading, and you need to be careful both in terms of the corrosion data that's out there, but also in terms of the lining materials, because there could be a difference between one flexible PVC grade and another. From a chemical composition, as you see here, we're starting to replace some of these hydrogens, and in this case with PVC, you can see 1 of every 4 hydrogens is replaced with a chlorine molecule. Now we move on to the first of the partially fluorinated materials. I talked a little bit about PVDF, polyvinylidene fluoride already. The picture on the right or diagram shows the homopolymer version. So you've got this this repeating chain that has 2 carbons, 2 hydrogens, and 2 fluorines. And the name partially fluorinated comes with the concept that we're starting to replace these hydrogens with fluorine. And there's the carbon-fluorine bond is one of the strongest single bonds in chemistry if we go back to organic chem. And that bond strength is what starts to give the fluoropolymers their temperature rating, their chemical resistance, and whatnot. PVDF itself, really good for strong acids. Does extremely well in a lot of acid services. It does not work well in basic solutions or concentrated alkalis, and there are some solvents that affect it. It's really easy to work with. We do it on a regular basis, and it is the most cost-effective fluoropolymer. Where it works, it makes a lot of sense. One of the, again, as we start looking at corrosion data and things to be aware of, PVDF, the homopolymer, which we're showing here, has a very high homologous, is extremely rigid. The difference in thermal expansion, the coefficient of thermal expansion between the steel structure and the lining material is significant. And then the rigidity of the homopolymer actually can lead to stress cracking from fairly gentle temperature swings. So the line steel market years ago moved from the homopolymer to the copolymer. Now, what does that mean to you guys? Well, a lot of the chemical resistant data that's out there is based on homopolymer stuff. So it's really important to understand when you're looking at something, and again, it's why you want to ask a lot of questions and go to various sources, is to make sure that it makes sense, and that where if you're specifying PVDF, understand that from a sheet lining perspective, it's going to be a copolymer, that the homopolymer is not available for lined steel. And that may or may not make a difference for a specific application. The next material would be ECTFE. Again, it's partially fluorinated. Looking on the right-hand side of the diagram, it is a copolymer. You've got that ethylene unit, the same as we had with HDPE, and then you've got the chloro-trifluoroethylene unit, the two carbons with 3 fluorines and a chlorine. And loosely speaking, they alternate, and you've replaced or substituted half of the hydrogens with a halogenated compound, mostly fluorine. This is more expensive than the PVDF, but now you've got a material that not only is it resistant to a lot of acids, it holds up well to most basic solutions as well, and a bunch of other solvents that PVDF doesn't hold up to. As I mentioned earlier, it's really good with spray coating, so you tend to see it as a baked and spray coating system. One of the challenges with ECTFE is globally there's one supplier that makes that resin. It's now Ciensco, formerly Solvay. It's sold under the brand name Halar, but there is only one global supplier. So when they've had problems with one global plant, when they've had problems, there can be an issue with supply. Another material very similar to ECTFE and partially fluorinated is ETFE. When sold by Chemours DuPont, it's known as Tefzel. Looking on the right, you can see it's the long carbon backbone. Again, you've got the ethylene unit, the two with the 4 hydrogens, and then a TFE, a tetrafluoroethylene unit with the 4 fluorines. So similar. The difference between this material and Halar is that it has all 4 fluorines, where Halar ECTFE has 1 chlorine and 3 fluorines. From a chemical resistance perspective, it tends to perform very similarly to as does ECTFE. There are challenges in getting a thick film spray coating, but this is a material that has been used and does extremely well for rotational linings. So it's not uncommon if you're looking at a rotolining application to end up with ETFE because it works really well. Again, chemical resistance is going to be very similar, and in most cases almost interchangeable with ECTFE. There are several manufacturers of the ETFE resin, but it's also the least available as a sheet lining material. So it's something that can be obtained, but it's usually not a material that someone has on their shelves sitting around. So it's not a major issue, but it's something to be aware of. Now we'll walk into the fully fluorinated materials. FEP was the first fully fluorinated melt processable thermoplastic. From a chemical inertness perspective, it's similar to PFA. When we talk about, so we started with the polyolefins and the PVCs, then went to the partially fluorinated polymers. When we talk about fully fluorinated, you can see the difference here in the chemical composition on the right side. There's no longer any hydrogen out there. So all of the hydrogen has been substituted with fluorines. And FEP is a copolymer of that TFE unit, the same one unit that we saw with the ETFE, and then we'll see with the other materials, and this HFP unit here with the 3 carbon chains and the 6 fluorines. It gives excellent chemical protection. The area that we don't see it used is in the high purity area. Most of the resin suppliers have focused on making high purity PFA grades, but from general chemical resistance, it's really good. The only caveat is that in hot HCl service, you tend to see surface blistering form with FEP, and you won't see it with some other materials. But it's a really good solution. It's a little less expensive than PFA, so where it can be used, it makes sense. And again, when we talk about this, the upper surface use on FEP by itself, we're showing here at about 200 degrees Celsius. From a lining perspective, we're considerably lower at about 300 degrees from a lining application due to the adhesive systems that are used. Therefore, in a lot of cases, there's no significant benefit to use PFA, and you can actually save money and have a more cost-effective solution. When you look at PFA, this was developed after FEP, and the upper surface temperature bumps up a little bit higher. So this was developed to be a melt processable version of the original Teflon PTFE material. Looking at the chemical composition, again, no fluorines. So you see that everything's been fully fluorinated. All the hydrogens are substituted. That branched material, the copolymer, is a little bit larger than the FEP unit. And the branchings would allow them to get to a bit higher temperature range here. What's to be noticed, or the other comment here, is if you've got high purity applications, there are several high purity grades that multiple resin suppliers use, and it allows for use where not only are you protecting the steel tank or the FRP from the chemical media, but you're actually using the PFA to provide a barrier from contaminating the chemical process where it's necessary in the semiconductor industry, possibly pharmaceutical industry, et cetera. Next material will be PTFE and modified PTFE. PTFE was the original Teflon material invented by Dr. Roy Plunkett back in 1938. It's a really difficult material to work with. It's not processed in the traditional way that the other materials that we've talked about. It's not melt processable. So whereas all the other materials we talked about have a true melting point, you can take pellets, put them into an extruder, melt them, and push or squeeze them into whatever shape you want. PTFE's got an extremely high molecular weight. It doesn't actually melt, and it has to be processed via some other unique systems that were designed just to handle that. So that's critical. PTFE is kind of a hybrid in between PFA or modified PTFE is kind of a hybrid between the PTFE and the PFA. So the diagram on the right shows you what PTFE looks like. It's just this really long carbon chain backbone with every hydrogen substituted. So same concept as what we saw with polyethylene in the beginning, long carbon backbone, but here every hydrogen has been replaced with fluorine. What modified PTFE is this hybrid material in between the two. It's got the same copolymer additive that PFA has, but a much smaller amount. That copolymer tends to be really expensive, so this provides a more cost-effective solution from a material perspective to PFA. It gives you a little bit, it doesn't really truly melt, but it starts to flow a little bit. So it has better permeation resistant than PTFE, which tends to have voids. And because it does flow a little bit, the weldability is better. So you can get better welds with it, which improve the quality of the parts. With both PTFE and modified PTFE, because it doesn't flow when you're actually doing welding, if you need a weld rod or cap strip, we're actually using PFA in there to weld to the to those materials. It also, as a general point, the modified PTFE for bonded sheet linings, The material cost might be a little bit less, but the workability is challenging. So it's not uncommon that the PFA lining or a modified PTFE lining actually end up really close to each other, because you're trading off, you're adding some challenges with working and using the modified PTFE versus a bit higher material cost with the PFA. But a lot of people tend to think that it's a less expensive total solution because the material costs are lower. And just want to bring out that it's not necessarily the case. Yeah. Why does installation and quality matter? Say, even if you select the right materials, you've gone through the issue, you've talked to a bunch of resin suppliers, you've selected the right material, hopefully you've picked the right applicator. Weld quality is critical, and I'll talk a bit there. So when we look at it, first is how's the company trained their welders? Have they done a good job? What type of data do you have in terms of their qualification process? How are they monitoring and tracking their welders and their welding? But also weld locations. The design on the front end is really important. If you heard me mention in the beginning with the different testing of recommending adding a weld sample in to be tested, the welds are typically the area that problems occur first. So location of those welds becomes really important. If you can put the welds into an area that see less stress overall, then you can maximize your chance for success. So you've got weld quality and weld location that are important. Cost versus performance. It's not always the easy answer is always, well, spend more money and get the higher performing material. Well, that's not always the best solution. We're trying to provide the most, and for your company, you're trying to provide the most value that you can get. So what's the total cost of life expectancy? But also, it's not always cut and dry that the higher performing or higher cost material will give you the highest performance. And finding the right applicator and understanding how they're going to build it and what their quality control manners is critical. Cutting corners on fabrication will lead the best design and application to failure. Yeah. Additionally, field repair. Something's been in service. It's working. There's a problem. Is the system designed where you can get in and repair it? With the sheet lining materials of vessels, we need to have access when we actually do the lining to be able to go inside, get our hands on everything, and line it. Certain technologies, again, rotolining, which is a good technology, may give you the ability to line the vessel in one piece without having a manway access, which sounds really good on the front end, but then if and when there's a problem, you can't get in and inspect it, and you can't get in and repair it. So you're stuck with an expensive reline for the entire thing instead of a repair. And does the installer applicator you have the capability either to go in the field and affect that repair, or can they bring it back in and do the repair in-house? But understanding not only how is it going to be built today, but how is it going to be serviced over the next 5, 10, 15 years really is important in getting to a successful solution for you. Our expertise at Electrochemical is in bonded sheet linings. In the past, we have done spray applied coatings, both dispersion and powder. We have gravitated towards the sheet lining as our solution, in part because we found more success with it, more repeatability, and it's our core capability, and it's what we do well. Typical sheet thicknesses range from 60 to 180 mils. Most of our linings are between 90 and 120 mils. It tends to provide a really robust thickness that gives some protection against permeation, some against mechanical damage. As you get thicker, the sheets become more challenging to bend and form, so workability becomes more difficult, and it also the sheet lining material is expensive, so it tends to add costs. So we've done thicker materials, but the bulk of what we do and what we see in industry is between 90 and 120 mils. In sheet lining, I say it's good for medium to very large vessels. And medium, as I mentioned, our lining application process, both installing the liner and doing the welding, we need physical access to get our hands in and bond the sheets to the wall to do all the welding. So really small vessels that you don't have access to are problematic. Conversely, we can get to really large vessels. We have a contract with a customer right now to do field installation of a fluoropolymer of a couple fluoropolymer line vessels, and these tanks are being built in the field, will be 30 feet diameter, some odd feet tall, and we'll have a crew go out there and do the lining in the field. So where a lot of equipment you're limited to how big can you get into an oven or rotational lining equipment to be able to physically make it, how big can you ship it. In our case, once it's too big to ship, we can actually go on the field on site and apply the lining inside. I mentioned, and this goes back to asking questions of all the different suppliers. As you start talking to people, you'll start to find your applications, both the material and the different type of application types, finding the benefits and limitations. And that tends to quickly run you into where one or two materials or solutions is the best scenario. In terms of keys, the critical steps. In our case, we can line customer supplied equipment, whether it's new or existing, and we can act as the general contractor and also specify and have the metal built. In order to get a good lining system installed, the proper design and preparation is really critical. It's no different than putting on paint on drywall or wallpaper. If you haven't done the work to get the tape down right, get rid of all the, make sure there's no nail holes or anything, you end up with a subpar product. And making sure that the metal welds are full and continuous and ground smooth and flush, that there's a good radius on all edges, and that the surfaces are all smooth. There's no undercutting, no weld slag or splatter on there is absolutely critical in order of getting a good lining, getting good adhesion, and getting a successful lining system. And it's one of the things to point out is you need to be careful. If you look at it, the cost of metal for equipment that needs to be lined is always going to be more expensive than the cost of that same equivalent tank that doesn't need to be lined. So don't be surprised whether as a specifier you're looking at getting metal built, or if you're looking at having the applicator go out and source the metal. It's to be expected that metal is held to a higher standard than unlined metal. So it's something to be aware of, especially early on in the budgeting process. And getting a ballpark price for how much a carbon steel tank cost is going to be very different than how much a carbon steel tank cost for lining. In terms of surface preparation, in order, again, to be able to get good bonding, you need to make sure any greases, oil, or contaminants are removed prior to lining. Grip blasting to a white metal finish and putting on a really strong 3 to 5 mil anchor profile is critical for getting an adhesive system to bond to it. And then getting a primer coat applied to it immediately after blasting so that no rouging or rust starts setting in, which will limit the capability of bonding, is really critical and important. QA, QC, and this goes back into your qualification of vendors and looking at it. It's really important to understand with the installer that you're working with, what exactly do they have in terms of quality assurance, quality control? Is the company ISO 9000 certified? Do they have a quality control manual? Are you allowed to look at it? I can't speak for everybody. I can speak, electrochemical is ISO certified. While we won't send you a copy of our ISO documents and procedures, if you come to do an on-site audit, we're happy to have you sit down and you can go through all of our procedures. You can see the procedures that that we take step by step to line the vessel. You can see the procedures we have for welder qualifications and training, and you can also look and see what documents you will get upon completion to know that not only do we say we're doing everything, but we've inspected everything and how it's been inspected throughout. It's important to ask your, in terms of looking to qualifying your contractors, if you're going out there looking at fluoropolymer linings, how long has the company been doing these linings? How many square feet have they installed with this type of application, this specific material? Do they have references? again, going back to material recommendations, where does that data come from? How did either you or the end user decide on the specific material? Now, have they consulted with multiple sources? Is there any test data? Going back to certifications, I mean, it's really important to understand, and welding is one of the most critical points. That would be, as a end user specifier, that would be one of the things I would jump to, is trying to understand how does the company qualify their welding procedures and welders? What do they do? How's the training? If you're doing on-site installation, who's the supervisor? What is their background? What types of documentation are out there in the quality systems? Are they spark testing it? Are they doing bond tests on the resin to make sure that they're getting good adhesion? Do they do a helium leak test to confirm that the lining's pinhole free? There's a whole bunch of stuff that's out there, but asking lots of questions is going to help you out. And I put this slide up, which I'm not going to go into a lot of detail, but if you get a copy, you can jump at it. You've got the DVS, which is the German Welding Society. It really is the holy grail. It's got, if you want to learn more about different plastic welding technologies and testing, it is the most comprehensive guide that's out there. It's published every 2 years. Odd year versions are in English, even years are in German. The AWS, the American Welding Society, has a couple of good guides. It's a little less expensive. You can get some of the information. Most of it was actually based from the DVS when it was only available in German. ASME RTP1, that's focused mainly on FRP vessels. There is a mandatory appendix on dual laminate vessels where it talks about the design for the lining components, the thermoplastic material. It's not exactly apples to apples for what line steel does, but there's a lot of really good pertinent information that might help you understand better and a little bit about the lining process as a whole. And finally, there's MTI, and Knight Materials is a member. The Materials and Technology Institute is a fantastic warehouse of data and information. It's a nonprofit organization founded back in 1977 with a mission to maximize member asset performance by providing global leadership in materials technology, improving safety, reliability, sustainability, and profitability in process industries. And here, even as a non-member, there are publications like the Plastic Repair Welding and the Guide for Repair and Alternation of Lined Equipment that might be really interesting to some of you folks. And as a member, you get all of that for free, but it's not an inexpensive membership. So I appreciate everybody's time. My contact information is here, and I guess we've got a few minutes for Q&A. Cindy?
Yes, we've got, and if you want to click on the chat too, Michael, you'll be able to see them, but I'll read the first one here from Francisco. He said, "Hi, Michael, wonderful presentation as usual." He's actually asking a question that's about slide 8 on material selection, most precisely about recommendations from resin suppliers. We've seen some engineering companies sticking to their suggestions and consider it as sacred word. Just like you say, the transformer and fabricator installer perspective need to be addressed. And I want to know your opinion about what's the best way to tackle this situation that may lead to some bad problems.
No, Francisco, great question. Appreciate it. So, yeah, I mean, it's really challenging. I mean, at the end of the day, and I know where you are and where I am, I mean, if somebody specifies a specific material, we're kind of stuck with it. But trying to explain data is always helpful. I mean, in my experience, if someone's set and I think that there's a problem, and I guess I go back to the application I mentioned where the plant was originally in the Gulf Coast and they were going to Canada. I didn't want to be the one going to the chemical plant and saying, I think we've got a problem with this because you specified PVDF, but I think Canada is an issue and I don't want to be in the middle. I went actually to the resin manufacturer and had a long discussion with them. When they agreed with me, then I responded back to the customer with my information saying that I'd been in contact with the resin supplier, and they went ahead and agreed and changed the materials. And the resin supplier was actually on board with being willing to have a discussion with them. It's always tricky. I mean, in some cases, we'll present multiple options. So we'll give them what they want in terms of what they've asked for, but we'll also can give them what they're requesting in terms of, or what we think might be a better solution or an alternate solution, and then try to have a discussion with them about it. But thank you.
Okay, and this one has several parts to it. So again, if you can click on the chat and read it, I'll read the first part. It's from Sam, but I don't know, you're the expert on this. If you can answer all of those in one. He says, can you make a few highlights on fluoropolymers and fluoropolymers are made and how the manufacturing process impacts the application? As for permutation and mechanical properties, for PTFE, isostatic molding versus paste extrusion.
Oh, wow. Sam, good to see you. And as always, really nice questions. So, I mean, I'll tell you that this is probably best offline and happy to go. But in general, you're right. I mean, isostatic molding would be a preferred method from my perspective. And I've got no skin in the game on this anymore. But that gives you what should be the most uniform and permeation resistant type of configuration. Paste extrusion, you're adding some sort of solvent system in with the PTFE in order to push it as you push it through a piping system in order to make the pipe. I tend to think or my expectation would be that as that solvent evaporates or comes out of the system or is baked out during the sintering process, that you're left with voids. So I would be preferential to the isostatic molding. Oh, wow. Your next one, PVDF. Again, really good questions. And it would be, emulsion polymerization versus suspension polymerization. This one, I worked for Solvay for a decade, who made a suspension emulsion polymerization. So I've got a little bit of bias on that side. What I would say is, in my 30 years of experience, I have yet to see an application that made a difference on PVDF, whether it was emulsion or suspension polymerization, in terms of how it's made. The end product ends up being roughly the same. The rheology might be a little bit differently. So trying to mold, quote, two compatible grades, you might get a slightly different shape or size. But the end product, if you make a sheet of 1/2-inch PVDF, whether it's emulsion, polymerization, or suspension, the mechanical properties, chemical resistance is going to be identical. And there's some differences possibly in how it may change in color over time in certain surfaces. The suspension one traditionally turned a little bit darker brown in hot acid service. However, the emulsion, now that they had to move away from a PFSA-based emulsion ingredient, is browner to begin with. So I would say that would be the least of my concerns is what type of polymerization. Be more concerned on the specific grade, whether you need a homopolymer or a copolymer. Let's see. And then your last one, rotolining, when it comes to where Tefzel excelled. Yeah. Let's see. I'm not quite sure what you mean on that one, Sam, but I'll follow up with you after this. I think we're starting to run out of time, Cindy.
Yes, we're at the end. Like I said, we're going to email out the presentation and the recording, and Michael can get with you, Sam, and answer some of those final questions for you. And again, thank you, Michael. Great presentation. And thank you all for joining us. We'll send this out to you shortly. Thank you.
Thank you.